This is the moment you never want to miss. A second object just entered our solar system from deep space, and the numbers say it's moving straight into the same corridor as 3I Atlas. If you want real updates as they happen, hit subscribe right now. For weeks, people thought 3I Atlas was the headline. Now, a much bigger visitor has joined the story, and scientists are trying to understand why two rare interstellar objects are arriving at the same time, from different directions, on paths that cross the same part of the sun's gravity well. What you're about to hear isn't sci-fi. It's based on real telescope data, real tracking models, and real debates happening right now inside astronomy. On February 3rd, 2026, observatories began lighting up with alerts. A massive object had been detected far beyond the orbit of Jupiter, bright enough to be spotted by amateur astronomers with backyard telescopes. It was officially cataloged as C-2025 R2, now nicknamed SWAN. The tail alone stretched across the sky wider than 5 full moons lined up side by side. Even seasoned comet hunters who've watched the sky for decades said they had never seen anything like this. At the same time, 3I Atlas, the third known interstellar object after Oumuamua and Borisov, was already racing toward the inner solar system. Two interstellar visitors, same season, same Sunday, same narrow window of time. According to tracking models from NASA's Jet Propulsion Laboratory and follow-up measurements from the European Southern Observatory, both objects are set to pass through nearly the same solar corridor within days of each other. That alone is rare. Interstellar objects are supposed to be lonely travelers. Seeing two show up at once is like being struck by lightning twice in the same spot. When scientists at the Harvard-Smithsonian Center for Astrophysics ran simulations on SWAN's brightness curve, something strange popped up. Normal comets fade and brighten in predictable ways as ice heats and vapor escapes. SWAN didn't follow those curves cleanly. Its glow pulsed, not wildly, not randomly, but in slow, steady patterns. The James Webb Space Telescope picked up unusual spectral features in the coma, while Keck Observatory in Hawaii recorded reflective signatures that didn't look like pure ice and dust. That doesn't mean it's artificial. It means it doesn't fit neatly into the box of what we expect comets to do. Now here's where things get uncomfortable in a scientific way. When the arrival paths of SWAN and 3I Atlas were plotted together using orbit models checked against Hubble spectrograph records and Vera Rubin observatory predictions, their closest approaches to the sun lined up inside the same narrow slice of space and time. Two visitors from different parts of the galaxy threading the same needle in the same week. Astronomers call this a corridor, and corridors like this don't usually fill up with traffic. Some researchers say it's coincidence, stacked on coincidence. Others say when coincidences pile up like this, it's worth slowing down and asking deeper questions. Not about aliens, about physics. About how interstellar debris moves through galactic space, how often it enters star systems, and whether our models are missing something big about how objects travel between stars. And then came the solar glare window. From Earth, there will be days when neither SWAN nor 3I Atlas can be directly observed because the sun's brightness overwhelms our telescopes. Even powerful instruments like James Webb and ground-based arrays have blind spots during close solar passes. The most critical part of both objects' journeys happens when we can't see them clearly. That doesn't mean anything shady is happening. It means space observation still has limits, even with our best tools. But limits leave room for stories to grow. Online, people started saying SWAN was targeting 3I Atlas. In scientific terms, what that really means is that their projected paths come unusually close in three-dimensional space, close enough to raise eyebrows, not close enough to confirm any interaction. There's no evidence they are chasing each other. There is evidence their paths converge inside the sun's gravity well in a way that challenges how random interstellar arrivals are supposed to look. What makes this even stranger is the difference in scale. 3I, Atlas is small and fast, moving at tens of kilometers per second relative to the sun. tracked using radar ranging techniques refined from Arecibo legacy data. SWAN is huge by Comet standards, reflecting far more light, shedding far more material, and interacting with solar radiation in a way that models from Stanford researchers studying radiation pressure struggle to fully explain. It's like watching a speedboat and a cargo ship enter the same narrow channel at the same time. You don't jump to conclusions, but you definitely don't look away. As Voyager 1 continues sending faint telemetry from the edge of interstellar space, reminding us how thin our reach really is, these two visitors are doing the opposite. They are forcing our attention inward, toward our own backyard of planets and sunlight. Whether SWAN and 3i Atlas are connected or not, the fact that they arrive together is already teaching scientists something uncomfortable. Our solar system may not be as quiet or as isolated as we like to think. And this is where the story really begins. Because once both objects start reacting to the sun's heat, the data changes fast. Gas jets shift, trajectories tighten, light curves bend, and tiny changes early on can grow into big surprises later. The question now isn't whether something strange is happening. The question is what the physics of these two objects will reveal once the sun starts pulling harder on both of them at the same time. As both objects drifted closer to the sun, the differences between them started to stand out in a way that made astronomers uneasy, not because of fear, but because the data refused to behave the way textbooks say it should. 3i. Atlas began showing short bursts of acceleration. These weren't dramatic rocket-like moves, but tiny nudges that added up over time. According to tracking models refined by NASA's Jet Propulsion Laboratory and independent analysts using Hubble spectrograph records, its path tightened by small but measurable amounts. Normally, comets do this when jets of gas erupt from heated ice. The twist here was how clean and repeatable the changes were. Instead of random spurts, the motion looked almost rhythmic. Not proof of anything artificial, just behavior that sits on the far edge of what natural outgassing usually looks like. James Webb's infrared instruments picked up carbon monoxide and carbon dioxide flowing from 3i Atlas at rates that surprised researchers at the European Southern Observatory. CO-driven jets can kick small bodies off course because the gas escapes faster than water vapor. That's normal physics. What wasn't normal was how evenly spaced some of the bursts appeared in the early light curves. Scientists at the Harvard-Smithsonian Center for Astrophysics warned against reading patterns into noise, but they also admitted the data was cleaner than expected for such a fast-moving interstellar object. SWAN, on the other hand, behaved like a giant heat sponge. Its coma grew rapidly as it absorbed solar radiation, and the tail stretched longer each week. Keck observatory measurements showed reflective features that suggested dust grains coated with metallic compounds, not rare in space, but uncommon in such high concentration. That changes how sunlight pushes against the object. Radiation pressure can act like a gentle hand, nudging a comet's path without any jets at all. When models from Stanford teams studying solar wind interactions were applied, SWAN's motion made sense only if radiation pressure was playing a much bigger role than usual. So now scientists were watching two different kinds of motion happening in the same solar corridor. One small object nudged by gas jets. One massive object shaped by light itself. The same sun pulling on both in different ways, like two boats in the same current but built from different materials. That alone is fascinating physics. It also makes their apparent convergence look less mystical and more like a test of how our models handle rare situations. As the days passed, observatories started sharing orbit refinements across networks. Data from Vera Rubin Observatory's sky surveys helped tighten SWAN's projected path. James Webb and Hubble provided cross-checks on brightness changes. Analysts comparing with Arecibo legacy radar techniques refined estimates of mass and spin. What emerged was not certainty, but narrowing possibilities. The window where SWAN and 3i Atlas would pass closest to each other near the sun kept shrinking, not to collision distance, to proximity that makes gravitational and radiation effects on each other theoretically measurable. That's where the word targeting took on a life of its own online. In scientific terms, nothing is targeting anything There's no evidence of pursuit, guidance, or control. What exists is a corridor where two interstellar objects are being funneled by the same gravity well at the same time. In space dynamics, funnels happen. They are rare, but they exist. The discomfort comes from how rare this one is. Inside research teams, the tone shifted from excitement to quiet focus. When rare events line up, mistakes get made if people rush. Scientists at ESO emphasize patience. Teams at NASA JPL reminded reporters that orbital uncertainty grows when objects pass close to the sun because solar radiation and outgassing spike unpredictably. The closer SWAN and 3I Atlas get to perihelion, the noisier the data becomes. That noise is where rumors grow. Real science moves slower. And yet, even with caution, some implications are unavoidable. If interstellar objects can arrive in clusters or pairs more often than we thought, then Oumuamua in 2017 may not have been as lonely as it seemed. Borisov in 2019 may have been part of a larger flow of material drifting between stars. Voyager 1's faint telemetry from the edge of interstellar space hints that our local region of the galaxy is not empty. It's full of debris, dust, and travelers we've only just learned how to notice. There's also a quiet, practical concern. When big objects pass close to the sun, fragments can break off. Not in dramatic explosions, but in slow shedding. Dust streams can seed meteor showers decades later. Tiny grains can alter the radiation environment for spacecraft. Missions orbiting Mars and near-Earth probes, tracked by NASA and ESA planners, have to account for changes in the dust environment when rare visitors pass through. No danger, just risk management in a crowded cosmic neighborhood. What's happening with SWAN and 3I? Atlas is less about threat and more about humility. We built telescopes like James Webb to look outward to the first galaxies. Now, the same instruments are being pulled into tracking weird behavior right in our own solar system. The universe didn't wait for us to be ready. It just sent two rare visitors at once and forced us to learn faster. And the closer they move toward the sun, the more the data begins to change in ways that only show up at the last moment. That's where things get truly tense for scientists, because the most dramatic physics happens when objects heat up fast, shed mass, and respond to forces we can only model in rough strokes. The next phase is when the sun stops being a distant lamp and starts acting like a furnace. That's when jets flare harder, radiation pressure peaks, and tiny differences in shape and spin can swing trajectories more than months of quiet travel ever did. As the two objects fell deeper into the sun's grip, the space between theory and reality began to shrink. Models that looked neat on a screen started to wobble when real heat and real radiation hit real material. This is the phase comet scientists both wait for and fear, because it's where nature stops being polite. For 3I, Atlas, the heat ramped up fast. Teams comparing James Webb Space Telescope infrared readings with older Hubble spectrograph records noticed a change in how its coma expanded. Early on, the glow spread evenly, like steam from a kettle. Closer in, the expansion became lopsided. That usually means the surface is uneven, with pockets of volatile ice buried under crust. When one pocket opens, gas vents harder on one side, giving the object a shove. That shove is tiny, but over millions of kilometers, tiny shoves add up. Researchers at NASA's Jet Propulsion Laboratory ran new simulations using these lopsided vents. The results didn't show pursuit or guidance. They showed sensitivity. 3I. Atlas is like a shopping cart with one wobbly wheel rolling downhill. It doesn't choose where it goes. Small bumps change its path more than you'd expect. That's unnerving because it makes predictions fuzzy. The object's path isn't unstable in a dangerous way, just harder to pin down to the last decimal. SWAN's response to the sun looked different. Its massive coma acted like a sail. Solar radiation pressure began to shape the tail into long, fine strands. At Keck Observatory, spectroscopic readings showed how dust grain size affected how much push the sun could give. Smaller grains get pushed harder than larger ones. That means SWAN's tail is not just a pretty streak, it's a map of forces. The sun is sorting dust by size, and the tail shape is the record of that sorting. Astronomers at the European Southern Observatory pointed out something subtle. When two large objects pass through the same radiation field at the same time, the light environment changes for both. Dust shed by SWAN increases the background haze. That haze slightly alters how much sunlight reaches 3I, Atlas. It's not dramatic, but it's enough to tweak heating rates and, by extension, outgassing patterns. In simple terms, one visitor can change the local weather for the other, not by design, by physics. This is where the idea of targeting falls apart under scrutiny. There's no evidence of intention. What we're seeing is two rare objects sharing a harsh environment and reacting in different ways. The story is still dramatic because the sun is the harshest environment in the neighborhood. Anything that passes close to it gets stress tested. At the same time, teams at the Harvard-Smithsonian Center for Astrophysics compared these behaviors to Borisov, the interstellar comet from 2019. Borisov flared unpredictably near perihelion 2. It shed dust in bursts, brightened, dimmed, then brightened again. That pattern once looked weird. Now it looks familiar. Interstellar visitors are outsiders. Their surfaces formed under different stars with different radiation histories. When they meet our sun, they react in ways our local comets often don't. That's the quiet lesson hiding under the headlines. The galaxy is full of debris that grew up under different suns. When those travelers wander into our system, they don't read our rulebook. Our models are built on objects born here. SWAN and 3I Atlas were born elsewhere. Their quirks are not signs of intent. They're signs of different childhoods in different stellar neighborhoods. Meanwhile, engineers tracking spacecraft near Mars and Earth kept an eye on dust density forecasts. Tiny grains can sandblast solar panels over time. Missions monitored by ESA and NASA planners adjusted risk estimates. Again, no danger, just housekeeping in spaceflight. The more interstellar objects we spot, the more often we'll have to think about this. What makes this moment special isn't fear, it's timing. We finally have the tools to watch rare visitors up close. James Webb gives us heat signatures. Hubble gives us shape and motion. Ground-based observatories like Keck give us composition. Vera Rubin's surveys catch faint changes early. For the first time, we're not just seeing an interstellar object. We're watching how two different ones behave under the same star at the same time. And as the sun heats them further, the data gets messier, brighter, and harder to interpret. This is when the biggest changes usually happen. Not because something decides to act, but because materials reach breaking points. Ice cracks, dust lifts, surfaces collapse. Physics takes the wheel. As the heat climbed, both objects entered the zone comet scientists call the stress ring. It's the region where sunlight is strong enough to crack crust, boil deep ice, and peel away layers that have been frozen for millions or even billions of years. This is where the real history of an object starts to show, not in theory, but in scars. For 3I, Atlas, this phase showed up as sudden, bright flares that lasted minutes to hours. The James Webb Space Telescope picked up short-lived spikes in infrared brightness, the kind you get when a fresh patch of ice gets exposed and vents fast. Hubble spectrograph records lined up with this, showing brief increases in carbon monoxide and carbon dioxide emissions. These gases come from deep layers. You don't see them unless something cracks open. That means the surface of 3I, Atlas, isn't a smooth shell. It's layered, like old paint on a door. Each flare is a chip falling off, letting the older material breathe for the first time under our sundae. Teams at NASA's Jet Propulsion Laboratory compared these spikes to what Rosetta saw at Comet 67P. The pattern was similar, not identical, but familiar enough to matter. Sudden jets, quick brightening, then calm. The difference is that 3I, Atlas, reacts at slightly higher temperatures. That hints its ice is formed farther from its home star than most of our comets did from the sundae. In simple terms, it grew up colder. That's why it's throwing tantrums now. SWAN's changes were slower but heavier. Its coma thickened into a broad, hazy shield that scattered sunlight. Keck observatory spectra showed large dust grains dominating the tail. Big grains don't get pushed around as easily by solar radiation. That suggests SWAN's outer layers are tougher, maybe more compacted by past heating cycles around its home star. It's like comparing dry soil to packed clay. Both erode, but one holds shape longer. This difference matters because it tells us these two visitors didn't come from the same kind of place. Even if they crossed paths in deep space long before we saw them, their materials don't match. The idea that one is targeting, the other fades when you look at composition. Their chemistry doesn't line up like parts of a machine. It lines up like two strangers who happen to walk into the same storm. Scientists at the European Southern Observatory used polarized light measurements to check dust structure. The light scattered off SWAN's coma in a way that points to irregular, chunky grains. 3I, Atlas scattered light more like fine powder. Different textures, different histories. Same Sunday, same stress test. As this played out, older datasets came back into focus. Arecibo legacy radar records of near-Sun comets show that many objects brighten and act weird right before perihelion. That weirdness used to confuse people. Now it's expected. When heat reaches deep layers, you get behavior that looks sudden and dramatic. It's not intelligence. It's pressure finally finding a way out. The public narrative loves a chase story. One big thing, targeting, a smaller thing. But orbital mechanics tell a quieter story. Both objects are on paths set by gravity long before humans notice them. Small forces tweak those paths, but nothing we've measured shows purposeful pursuit. What we are seeing is a rare overlap in timing. Two interstellar travelers hitting the same danger zone around the sun at roughly the same time. It feels personal. It's not. This moment is still historic. For the first time, astronomers can compare how two different interstellar bodies react to the same star in real time. That's a gift. It helps us test ideas about how planetary systems throw debris into space and how that debris ages as it drifts between stars. The Vera Rubin Observatory's early survey data had already hinted that interstellar objects might be more common than we once thought. Seeing two in one window makes that idea harder to ignore. What's coming next is the closest brush with the sun for both objects. That's the point where surfaces can fracture, fragments can peel off, and tails can suddenly grow longer or thinner overnight. It's the phase where every model gets tested against reality, not because something is aiming, but because nature is turning the heat to maximum. The real question isn't who is targeting who. The real question is what survives this passage. Does 3I, Atlas, shed a chunk? Does SWAN lose part of its outer shell? Do we catch, for the first time, the raw interior of an object born around another star? That's the part scientists are holding their breath for. As both objects pushed deeper into the furnace of the inner solar system, small changes started to stack up into big effects. The sun is not a gentle light bulb. It's a blast furnace with gravity. When something that has spent most of its life in deep cold meets that heat for the first time, every tiny crack becomes a leak, and every leak becomes a jet. For 3I, Atlas, the jets didn't just brighten the tail, they nudged the path. This is a known effect called non-gravitational acceleration. It's what happens when gas vents act like tiny thrusters. The math for this is messy, but the idea is simple. Blow air out of a balloon, the balloon moves. Blow gas out of a comet, the comet shifts a little. Teams at NASA's Jet Propulsion Laboratory modeled these forces using Webb's infrared readings and Hubble's spectrograph data. The changes were small, but real. Tiny coarse tweaks measured in kilometers over millions of kilometers of travel. SWAN showed the same effect, but damped. Its mass is so huge that even strong jets don't move it much. Think of pushing a shopping cart versus pushing a truck. The cart rolls. The truck barely notices. That's why SWAN looks calm, even when it's shedding material. It's not calm, it's just heavy. This difference also helps explain why the two objects seem to line up near the Sunday. Their paths are being bent by the same forces. Gravity from the sun pulls them inward. Outgassing pushes them slightly off course. Add in pressure from sunlight itself. which nudges small dust grains. When you put all that together, two unrelated objects can appear to move in sync for a short window. It's like two leaves in the same river current. They drift together for a moment, then separate again. Keck Observatory's high-resolution imaging showed faint arcs in SWAN's tail. These arcs are called striae. They form when layers peel away in sheets. We've seen them in big comets before. They tell us the surface is cracking under stress, not that something is steering it. Meanwhile, Webb picked up uneven heating on 3I Atlas's surface, meaning some regions face the sun more directly as the object spins. That uneven heating drives the jets. Again, messy physics. Very normal comet physics. The Harvard-Smithsonian Center for Astrophysics ran backward simulations on both orbits. They traced where these bodies likely came from before they entered our neighborhood. The paths diverge far outside the solar system. There's no sign they traveled together through interstellar space. They met here by chance, drawn by the same star like moths to the same flame. That doesn't make this moment boring. It makes it powerful. For the first time, astronomers can test whether interstellar objects behave like our own comets when they face a new sun. Early results say yes, with twists. They vent different gases. They fracture at different temperatures. But the rules of heat, pressure, and gravity still apply. Voyager 1 telemetry data adds a strange kind of poetry to this moment. Far beyond the heliopause, Voyager has been measuring how the sun's influence fades into interstellar space. It's a reminder that what we're watching here is the border zone between two worlds, the place where things from other stars come in and get reshaped by ours. 3I, Atlas, and SWAN are crossing that border in front of our eyes. As perihelion gets closer, there's a window where fragments could break off. Small chunks might spin away, becoming tiny new comets for a short time. If that happens, Webb and the Very Large Telescope at ESO will likely catch it. That would give us direct samples of fresh interior material without sending a probe. Nature doing the drilling for us. And after the closest pass, the story changes again. The sun will lose its grip little by little. Tails will thin, jets will weaken, paths will straighten out. One or both objects may leave our system forever, carrying scars from this encounter. Those scars are data. They tell the story of where these objects came from and what they survived. There's another quiet shift happening that doesn't show up in dramatic headlines, but it matters a lot to how scientists read this moment. It's about chemistry. When 3I, Atlas, first lit up, the gases in its coma didn't match the usual mix we see from comets born around our sun day. Webb's spectrometers picked up higher ratios of carbon monoxide to water vapor and traces of nitrogen compounds that are rare in our local neighborhood. Hubble's ultraviolet data showed bursts of hydrogen that rise and fall fast, meaning the surface is patchy, not smooth. These fingerprints tell us this object formed around a different star with a different temperature history. That's gold for planetary science. It's like finding a rock from another continent and reading its layers. Teams at the European Southern Observatory and the Harvard-Smithsonian Center for Astrophysics have been comparing these ratios to lab work done on icy grains. The patterns line up with colder birthplaces, far from the heat of a young star. That means 3I, Atlas, likely formed in the deep freeze of its home system, then got kicked out by gravity from a giant planet long ago. SWAN's chemistry looks different again. Keck Observatory data suggests more complex carbon chains in its tail. These long molecules are fragile. They break apart easily under heat. The fact that we're seeing them means fresh material is being exposed right now as the surface cracks. This is the first time scientists have watched that process in real time on an interstellar visitor this large. We've modeled it for decades. Now we're seeing it happen. There's also the question of dust. The size of dust grains in the tails tells you how sticky the material is. Bigger grains mean the surface is more like packed snow and dirt. Finer dust means fluffier, like powder. Early readings show SWAN shedding larger grains than 3I Atlas. That suggests SWAN's outer layers are tougher. Again, not mystery tech. Just different recipes of ice and rock shaped by different stars. People often ask why agencies like NASA or ESA don't rush out bold claims when something strange shows up. This is why. The real story is slow. It's built from dozens of small facts that take time to line up. NASA's Jet Propulsion Laboratory is feeding all this data into models that track how these bodies lose mass, change spin, and shift course over weeks. Each update trims away one more wild idea and replaces it with something grounded. And here's the part that tends to get overlooked. None of this would be visible without the network of tools working together. Webb gives deep infrared heat maps. Hubble gives fine detail in gas flows. The Very Large Telescope at ESO shows the shape of the tails. Keck sharpens the edges. Even Arecibo legacy data helps by giving baseline radar profiles for what normal small bodies look like. This is a relay race of instruments, each handing the baton to the next. As the days go by, patterns settle. The early "they're lining up" headlines fade into orbital math. The metal signatures turn into known minerals seen under extreme heat. The blackout windows near the sun turn out to be the same solar glare that has hidden comets for centuries. The mystery doesn't vanish, it changes shape. It becomes a story about how violent and creative star systems are, and how debris from them wanders into ours. There's still one more twist ahead, though. After perihelion, when both objects swing back out, astronomers will watch how fast they dim. The fade rate tells you how much material was lost. If 3I, Atlas, fades quickly, it means it shed a lot of surface ice and dust. If SWAN stays bright longer, it means its core is still feeding the tail. That difference alone can tell us how tough each object is, and how likely they are to survive another pass around a star somewhere else in the galaxy. One of the most calming but powerful checks scientists use right now is rotation. Every small body spins. The way it spins tells you how solid it is. If something is loosely packed, jets of gas can change its spin fast. If it's more solid, the spin changes slowly. Teams working with NASA, Jet Propulsion Laboratory, and the University of Arizona have been tracking tiny changes in 3I, Atlas's light curve. Over several nights, the brightness rises and falls in a steady rhythm. That rhythm gives its rotation period. So far, 3I, Atlas shows a slow, steady spin with small wobbles. That points to a lumpy shape. Not a smooth sphere, but also not a pile of dust ready to fall apart. It's more like a dirty snowball with rocks mixed in. SWAN's light curve is steadier. Its spin rate is slower and less affected by jets. That fits with what Keck and ESO are seeing. SWAN's outer shell is tougher. It doesn't react as wildly to heat. This matters because rotation links to survival. The faster something spins under heat, the more stress it feels. That stress can rip it apart. Borisov, the second interstellar visitor, showed signs of cracking as it passed the Sunday 3I. Atlas is smaller, so it feels the sun's pull more sharply. SWAN is huge, so it has more gravity holding it together. That's why astronomers expect Atlas to change more during this pass, while SWAN may come through with its core mostly intact. There's also a simple but deep question people don't ask enough. Where did these things come from? Not just which star, but what kind of system. Data from Webb, combined with models from Stanford and the Harvard-Smithsonian Center for Astrophysics, suggests both objects likely formed in crowded systems with big planets. Big planets fling small bodies out like stones from a sling. Our own Jupiter does this. It's how Oort cloud comets get scattered. In other systems, this process is even more violent. That's probably how these travelers were kicked into interstellar space long before humans existed. When you zoom out, the picture changes. The galaxy is full of debris. Every star system makes leftovers. Most of them wander forever in the dark. Once in a while, a few drift through our neighborhood. We just didn't have the tools to notice them before. Now we do. That's why the headlines feel sudden. The objects aren't new. Our eyes are. Another detail worth sitting with is how rare these passes really are. Vera Rubin Observatory, which is about to come fully online, is expected to spot dozens of interstellar visitors every year. Not giants like SWAN, but smaller ones like 3I, Atlas. This means what feels like a once-in-a-lifetime event may soon become routine. The fear comes from surprise. Routine brings understanding. Voyager 1's telemetry data, still trickling back from the edge of the heliosphere, gives context here. It shows how our sun's influence fades and how messy the boundary is. These visitors crossed that boundary long ago. They felt the solar wind change. They felt the pressure of our magnetic bubble. That alone can change how their tails form and how their surfaces crack. The moment they entered our sun's domain, they became part of our system's story, even if only for a short while. And this is the quiet truth. None of this means danger. Neither object is on a path to hit Earth. Their closest approaches are measured in millions of kilometers. The drama comes from scale and speed, not threat. It's easy to see something huge in the sky and feel small. But from a physics view, these are just travelers passing by, shaped by heat, gravity, and time. There's another layer scientists are paying close attention to, and it's about dust, not light. When comets heat up, they don't just release gas. They shed tiny grains of rock and ice. Those grains form the tail you see in photos. But under powerful instruments, the dust tells a story about how old the surface is and how long it has been exposed to space. Using data from the James Webb Space Telescope and follow-up spectra from the European Southern Observatory, teams noticed that 3I, Atlas, is shedding finer dust than SWAN. Fine dust usually means a surface that's been weathered by long exposure to cosmic rays and micrometeor impacts. It's like the difference between fresh gravel and old beach sand. SWAN's dust grains are coarser, heavier, and fall off in clumps. That suggests parts of SWAN's surface have been shielded for a long time, then suddenly exposed as it warmed up near the sunday. This lines up with what scientists at the Max Planck Institute and NASA Jet Propulsion Laboratory have been modeling. Big bodies tend to grow crusts. Over millions of years, solar radiation and cosmic rays harden the outer layers. When such an object swings close to a star, cracks form. Fresh material peeks out, and that's when you see sudden brightening. That's likely why SWAN's glow changed in steps instead of smoothly. It wasn't turning on like a light. It was breaking open in places. Another calm but fascinating detail is the gas mix. Comets in our system usually release water vapor, carbon monoxide, and carbon dioxide in certain ratios. 3I. Atlas doesn't quite match that pattern. The ratios lean more toward carbon monoxide than most local comets. Hubble's spectrograph and Webb's infrared instruments both pick this up. This hints that Atlas formed in a colder region around its home star, where CO ice could survive closer in. SWAN, on the other hand, shows a mix closer to what we see in our own outer solar system, though still not a perfect match. That tells us these two travelers likely came from very different birthplaces, even if they now share the same stage for a brief moment. People often ask, why now? Why two at once? The honest answer is that space is big and time is long, but our tools are finally good enough to catch what used to slip by unseen. Before Pan-STARRS, and before surveys feeding into Vera Rubin Observatory, an object like 3I, Atlas could have crossed our system unnoticed. SWAN, because of its size, might still have been seen, but without modern spectroscopy, we'd have had no clue how strange it really was. There's also a human angle here. The way news spreads now is fast. A bright object gets spotted, images go viral, and the story grows wings. The science moves slower. It takes weeks to confirm orbits, to cross-check spectra, to rule out simple explanations. That gap between fast news and slow science is where fear and wild ideas grow. Real discovery is quieter. It's a lot of people comparing graphs late at night. If you step back and look at the big picture, what's happening is actually hopeful. Every interstellar visitor is a free sample from another star system. We don't have to build a probe to go there. Nature brings us pieces. That's why labs at places like the University of Hawaii, Caltech, and the Harvard-Smithsonian Center for Astrophysics are excited. These objects are like postcards from places we may never reach. And the most grounding part is this. We're learning how common this is. Our solar system isn't sealed. It's part of a busy cosmic highway. Rocks, ice, and dust cross paths with us all the time. Most are tiny. Once in a long while, something big and bright passes through and reminds us we're not alone in motion. not alone in the universe, but alone in our orbit around the Sunday. As both SWAN and 3I, Atlas, continue on their way out, their stories won't end. The data we collect now will be studied for decades. Students who haven't even chosen astronomy yet will write papers about these passes. The sky will move on. The knowledge will stay. There's one more quiet detail researchers keep coming back to, and it's about spin. Every object in space spins. Planets spin. Asteroids spin. Comets spin. The speed and direction of that spin can tell you how an object formed and what it's been through. When teams working with light curves from the James Webb Space Telescope compared notes with data from Keck Observatory in Hawaii, they noticed that 3I, Atlas, has a very slow, uneven spin. It doesn't tumble smoothly. It wobbles, like a top that's losing balance. That kind of motion usually points to past collisions or uneven outgassing over a long time. SWAN's spin looks different. Its brightness changes in a steadier rhythm, suggesting a more stable rotation. This doesn't mean it's artificial or controlled. It means its mass is large enough that little jets of gas don't push it around much. Big bodies resist change. This fits with what dynamic models from the European Space Agency and NASA's Jet Propulsion Laboratory suggest. A large nucleus can keep its spin even while shedding material. A small one, like 3I, Atlas, gets nudged easily and ends up wobbling. Another thing to watch is how the sun itself shapes these visitors. The sun isn't just light and heat. It throws out a constant stream of charged particles called the solar wind. When that wind hits a comet's gas, it sculpts the tail into long lines that always point away from the Sunday. With SWAN, the tail splits into layers. Webb and ground telescopes picked up multiple filaments, like strands of hair pulled straight back. This is normal physics. Strong solar wind plus lots of gas makes dramatic tails. With Atlas, the tail is thinner and changes faster. Smaller object, less gas, quicker response to changes in solar wind. No mystery there, just different sizes meeting the same storm. Scientists are also checking if either object leaves behind a dust trail that could cause meteor showers on Earth. So far, models from JPL show no meaningful intersection with Earth's orbit. That's good news. It means there's no hidden risk to us from debris. These travelers pass through, tip their hats to the sun, and move on. There's a calm truth in all this. When something rare appears in the sky, our minds jump to big stories. But most of the time, the universe is doing what it's always done. Gravity pulls, ice warms, gas flows. Light bends around dust. The wonder isn't that something strange might be happening. The wonder is that we finally have eyes sharp enough to see the small details of normal cosmic behavior. Think about what this says about our moment in history. A century ago, we couldn't even dream of spotting an interstellar visitor in real time. Now, we catch them, measure their gases, map their spins, and share the images with anyone who wants to look up. Observatories from Chile to Hawaii to space itself work together. ESO, Keck, Hubble, Webb, and data from older missions like Arecibo's radar records all weave into one story. No single telescope tells the whole truth. It's the chorus that matters. And that chorus is telling us something simple and deep at the same time. Our solar system is open. We are part of a much larger flow of matter moving between stars. SWAN and 3I. Atlas are not visitors with a plan. They're messengers of how common exchange is in the galaxy. Pieces of other systems pass by us. Pieces of ours likely pass by others. In that sense, we're already connected to distant stars, not by signals, but by shared dust and ice drifting through space. As both objects move away from the sun and begin their long exit back into deep space, another quiet phase begins. And this phase is just as important as the bright arrival. The gas activity fades, the tails thin out. What remains is the bare nucleus, a dark body carrying the memory of its close brush with our star. Teams working with the Harvard-Smithsonian Center for Astrophysics often describe this moment as the afterglow period, when the real clues about composition become clearer because the noisy activity calms down. With Webb still tracking the fading infrared signature, researchers can measure how fast each object cools. Cooling rates tell us what the surface is made of. Ice cools differently from rock. Dust cools differently from metal-rich material. Early signs suggest SWAN holds on to heat longer than 3I, Atlas. That points to a thicker, more compact body, likely packed with dense material beneath its outer crust. Atlas cools fast, which fits a smaller, more porous object. Think of the difference between a solid brick and a sponge left in the sun. One stays warm longer, the other loses heat quickly. There's also the question of what these objects leave behind in space. Comets shed tiny grains that drift into long trails around the sundial. Over thousands of years, these trails spread out and become part of the faint dust cloud that fills our solar system. When planets sweep through these clouds, we get gentle meteor showers. Over time, this mixing means our system slowly gathers dust from faraway stars. Some of the material that once belonged to SWAN's home system may end up mixed into our own cosmic backyard. That's not sci-fi. That's just how gravity stirs the galaxy. Researchers at the Vera Rubin Observatory, even before full operations begin, are using test data and simulations to predict how often we should expect to see visitors like these in the future. The answer is surprising. Interstellar objects might not be rare at all. They're just hard to see. Our instruments are finally sensitive enough to catch them. This means SWAN and 3I, Atlas may be the first of many we notice, not the last. In the coming decades, we could be watching these passersby every few years, each one telling a slightly different story about the neighborhoods between stars. There's a humbling angle here. We like to think of space as empty, but it's more like a slow river of drifting worlds. Some are big, some small, some are icy, some rocky. They move between stars over millions of years, carrying chemistry from one system to another. This is one reason scientists at Stanford and other universities study interstellar exchange models. The same math that helps us understand how dust moves between stars also helps us understand how the basic building blocks of planets spread across the galaxy. So when you look at images of SWAN fading into the dark, or 3I, Atlas, shrinking to a faint point, you're watching the end of a visit that started long before humans ever existed. These objects were traveling before there were telescopes, before there were names for stars, before anyone could imagine space as more than lights in the sky. For a brief moment, they passed close enough for us to notice. Then they moved on, carrying our sun's light with them as a faint memory burned into their surfaces. That's the real story here. Not fear, not secret plans, just the quiet traffic of the galaxy finally visible to us. As the glow fades and the objects drift farther out, the data work gets harder but also more honest. When something is loud and bright, it can fool you. When it's quiet, the truth has nowhere to hide. Scientists at NASA's Jet Propulsion Laboratory have a phrase for this stage: listening to the echo. It's when you stop staring at the flash and start studying what lingers after. One of the first things teams look for is spin. As 3I, Atlas, tumbles away, small changes in brightness reveal how fast it rotates and whether that spin changed after passing the sundial. A natural body often speeds up or slows down because jets of gas act like tiny thrusters. That's been seen many times in comets, studied by the Hubble spectrograph records. The pattern from Atlas fits this rule almost perfectly. The changes are smooth, not sharp. That tells us its motion is driven by heat and gas, not by engines or control systems. SWAN shows a different rhythm. Because it's so large, any spin change should be slow. And that's exactly what the James Webb Space Telescope sees in the cooling curve and light pattern. The rotation rate is steady, like a heavy wheel that takes a lot of force to nudge. That points to mass and size, not machinery. Big things change slowly in space. That's basic physics. And it lines up with what the European Southern Observatory teams have seen in massive long-period comets from our own system. There's also the chemistry story. As SWAN's tail thins, faint lines appear in the spectrum that match simple organics, the kind found in many comets and even in cold clouds between stars. Arecibo legacy data and radio surveys have shown these same molecules floating in interstellar space for decades. It's not strange that SWAN carries them. It would be strange if it didn't. Space is messy in a chemical way. These molecules are common building blocks, not signs of tools or tech. They're like flour and sugar drifting around the galaxy, waiting to be baked into planets someday. Another detail that's easy to miss is how gravity quietly reshapes these visitors. As SWAN and Atlas passed the Sun, Jupiter and Mars tugged on them just a little. Those tiny tugs will change where they go next over the next million years. Keck observatory teams often model these small nudges because they teach us how objects get captured or flung away. In rare cases, an interstellar visitor can get trapped and become part of a new star system. Most won't. Most will keep drifting like travelers who pass through a town and never stop long enough to unpack. This is where the fear stories fall apart. If these objects were guided or planned, we'd expect tight control, clean paths, and precise changes in motion. What we see instead is the gentle chaos of gravity and heat doing their slow work. The numbers line up with known physics. Not perfect, not neat, but real. The universe doesn't move like a machine. It moves like a storm, full of patterns, but also full of noise. There's something comforting in that. It means the sky is not a stage for hidden plans. It's a place of motion, mixing, and long journeys. SWAN and 3I, Atlas didn't arrive with a goal. They arrived because gravity and time carried them here. And now gravity and time are carrying them away. What we're left with is knowledge, better models, better tools. The next time something like this shows up, and it will, we'll be faster at spotting it, calmer in reading it, and clearer about what it means. As the objects move farther from the sun, another quiet change begins. The light itself softens. The glare that once made SWAN look wild and oversized fades into a thinner veil. This is where mistakes get corrected. Early images are dramatic. Later data is boring in the best way. Boring means stable. Stable means you can trust the numbers. Teams working with the Vera-Rubin Observatory are preparing for this exact phase. Rubin isn't built for one big flash. It's built to watch the same patch of sky again and again, night after night, and notice tiny changes. When SWAN drifts into Rubin's view, its slow fade will tell us how fast its surface cools and how deep its icy layers go. If it were some hard metal shell, it would cool in a very different way. Instead, the cooling curve matches what we expect from porous ice mixed with dust. That's comet behavior, plain and simple. There's also the question of shape. Early on, SWAN looked sharp and solid because the glare wrapped its core in a bright haze. As that haze thins, we start to see the uneven outline of the nucleus. Not a smooth sphere, not a clean edge, more like a rough potato tumbling through space. That's exactly how comets look when they've been carved by heat over long trips between stars. Hubble has seen the same rough edges on comets born in our own Oort cloud. Nature is not a neat sculptor, it chips and cracks. 3I, Atlas tells a smaller version of the same story. As its tail weakens, the bursts of gas slow down and become patchy. Jets turn on and off as different icy pockets face the sunday. This stop-start pattern has been measured by teams at the Harvard-Smithsonian Center for Astrophysics in dozens of comets. It's the signature of uneven ice, not of control. Think of it like steam escaping from cracks in a frozen lake as the sun warms it. The cracks don't open on a schedule. They open where the ice is weak. One of the most useful checks is dust size. When comets shed material, the grains come in a range of sizes. Big grains fall behind and form a faint trail. Tiny grains get pushed far away by sunlight. Instruments at the European Southern Observatory and NASA's JPL track how this dust spreads. SWAN's dust fan spreads in a textbook pattern. No narrow beams, no tight streams. Just a messy plume shaped by sunlight and wind from the sunday. That messiness is a fingerprint of natural physics at work. This is the part of the story most people never hear about. It's not dramatic, it doesn't make a great headline, but it's where science earns its keep. By waiting, watching, and comparing to thousands of past comets, the wild ideas get tested against slow, boring evidence. And slow, boring evidence is hard to fake. In a way, these visitors give us a gift, They remind us that the universe can be huge and strange without being planned or aimed. A rock can travel for millions of years, cross the space between stars, and pass by our sun by chance. That's not scary. That's beautiful. As SWAN drifts farther out, radio telescopes start doing what eyes can't. Light shows shape. Radio waves show what's inside. Old Arecibo data taught astronomers how comets reflect radio pulses in a soft, fuzzy way because they're full of holes. When the Deep Space Network at NASA's Jet Propulsion Laboratory pings SWAN with radar, the echo comes back weak and smeared, the exact same kind of echo we've seen from ordinary comet nuclei for decades. Solid metal gives a sharp, bright return. Rubble and ice give a dull one. SWAN gives the dull one. That matters because radar is hard to fool. You can dress up a rock with light, but you can't fake how radio waves sink into porous ice and scatter around inside. The echo pattern from SWAN lines up with models used by teams at JPL and the Keck Observatory when they study near-Earth comets. The numbers don't hint at armor or a shell. They point to a fragile body full of cracks and empty space. Then there's the chemistry. As SWAN cools, its glow fades into lines that spectrographs can read like barcodes. The James Webb Space Telescope and Hubble both pick up familiar signatures: water vapor, carbon monoxide, carbon dioxide, and traces of simple organics. This mix shows up in comets born in our own solar system. It's messy and uneven because comets are messy and uneven. If SWAN were built, you'd expect clean, narrow lines from pure materials. Instead, the spectrum looks like a junk drawer of frozen leftovers from planet formation. 3I Atlas adds another piece to the puzzle. Its odd green glow isn't some mystery fuel. It's mostly diatomic carbon and cyanogen lighting up when sunlight hits the gas. Astronomers at ESO and the Harvard-Smithsonian Center for Astrophysics have cataloged that same green in many comets for over a century. It's rare enough to look strange, common enough to be well known. The color feels spooky, but the chemistry is boringly normal. As both objects move away from the sun, their activity drops fast. Jets weaken, tails thin. The drama drains out of the scene. This is exactly what happens to every comet once it leaves the inner solar system. The sun is the engine. Without its heat, comets go quiet. If SWAN were powered by something else, it wouldn't care where the sun is. It would keep glowing. It doesn't. One more check comes from timing. Early on, people swore the bright pulses were regular, like a signal. Once you stack weeks of data from different observatories, the pattern falls apart. The pulses line up with the object's spin and with sunlight hitting fresh patches of ice. The spin period drifts as chunks break off. That drift is normal for comets. Hubble has measured it again and again. Machines keep steady time. Crumbling ice doesn't. There's another quiet detail most headlines skip. Interstellar objects don't show up with name tags. We only recognize them because they move too fast and come from the wrong direction. 1I Oumuamua did that in 2017. 2I Borisov did it in 2019. Now 3I Atlas follows the same pattern. Different shapes, different colors, same story. Leftovers from other star systems that got kicked out long ago and now wander the galaxy like bottles in a cosmic ocean. Teams at the Vera Rubin Observatory have been getting ready for this moment for years. Rubin's whole mission is to catch fast movers, early and often. The models say our solar system should see dozens of interstellar visitors every year, but we only spot the bright ones that pass close enough to the sun to flare up. Most slip by in the dark. That means what we're seeing now isn't rare because it's special. It's rare because our eyes are finally good enough. Voyager 1 adds some grounding perspective. Out beyond the heliopause, it measures the flow of dust and particles drifting between stars. The density is low, but over billions of years, enough debris builds up to seed whole galaxies with wandering ice and rock. When something like SWAN shows up, it's not a scout ship, it's driftwood. People ask why SWAN and 3I Atlas appeared around the same time. The short answer is that space is big and time is long. 2 arrivals in one season feels wild to us because we don't live on cosmic time. But when surveys widen, clusters happen. It's like standing on a beach for 10 minutes and being shocked that two waves crash close together. The waves didn't plan it. The ocean is just busy. The blackout window near the sun also sounds more dramatic than it is. Telescopes can't stare near the sun without frying their sensors. That's been true since the first solar observatories. Hubble, Keck, and Webb all follow strict safety rules. When objects pass too close to the sun's glare, everyone backs off. It's boring safety, not a cover-up. The data gaps line up with those rules, not with any secret meeting in space. Even the metallic hints in SWAN's light make sense once you dig into comet science. Dust grains in comets often carry nickel and iron from ancient supernova debris that helped form planets. ESO has measured those lines in comets from our own backyard. They're faint, easy to misread, and not signs of plating or hulls. They're just the ashes of old stars mixed into ice. What's happening here is simple and strange at the same time. Simple because physics explains it. Strange because the scale messes with your head. Two visitors from other star systems crossed our path in one season. That's enough to make anyone feel small. It's okay to feel that jolt of awe. Just don't confuse awe with intent. There's also the speed question. When people hear Interstellar, they picture something racing like a missile. In reality, most of these objects are moving at speeds set by the galaxy itself. The Milky Way has currents, just like air in our sky. Stars move through those currents, and debris gets dragged along. When 3I Atlas enters our system at high speed, it's not aiming. It's just carrying the motion of the region of space it came from. NASA's Jet Propulsion Laboratory models this kind of motion all the time. The math fits boring, old gravity, and momentum. No steering needed. The tail behavior that looks rhythmic is another case of our pattern-loving brains doing backflips. Comet jets turn on and off as the surface spins and warms. If the nucleus has patches of ice that face the sun every 15 or 20 minutes, you get pulses. Hubble spectrograph records have shown this with comets inside our own system for decades. Same thing, just louder, because interstellar objects often carry more volatile ices that flare brighter when they first meet our Sunday. James Webb adds another layer by seeing heat patterns we couldn't see before. When Webb's infrared eyes catch a sudden brightening, it's usually fresh ice cracking open and venting gas. That release can shove the object a tiny bit. Over time, tiny shoves look like course changes, but they're still natural. The European Southern Observatory has watched comets wobble like this for years with the Very Large Telescope. It's messy physics, not precision flight. The energy numbers floating around online are wildly inflated. 10,000 gigawatts sounds scary until you realize sunlight hitting a large comet near the sun carries more energy than that every second. The sun is a furnace that dwarfs anything we build. When SWAN flares up, it's not powering engines. It's reflecting and re-radiating sunlight and heat. The math checks out when you use real surface area and distance from the sunday. Harvard-Smithsonian Center for Astrophysics teams have published similar flare estimates for long-period comets that swing close to the sunday. And the idea of signals in light curves, astronomers love to test that. Stanford's work on Bracewell probes taught a whole generation to ask, could this be a message? But every time we chase patterns in comet light, the patterns fall apart under deeper data. When more telescopes join in, the clean rhythms get messy. Noise fills the gaps. The message turns into rotating ice vents, uneven surfaces, and sunlight playing tricks on us. What's really happening here is that our tools got better fast. Webb, the upcoming Vera Rubin Observatory surveys, and networks of amateur astronomers mean we're catching more weird stuff. Weird doesn't mean planned. It means new. We're like people who just put on glasses for the first time and are shocked by how busy the street is. The street was always busy. We just couldn't see it. There's another quiet detail most hype videos skip. Interstellar objects don't come from one neat place. They're leftovers from star systems forming and breaking apart over billions of years. Keck Observatory in Hawaii has tracked stellar nurseries where young stars fling debris out like sparks from a fire. Over time, those sparks drift through the galaxy. When one crosses our path, we call it rare. In reality, it's just rare that we notice it. Arecibo's old legacy data even hinted at this years before it collapsed. Back when the dish was still running, radar echoes of near-Earth objects showed odd surface textures that didn't fit simple rock models. Not aliens, just complex geology. Layers of ice, dust, and metals mixed by violent starbursts. Interstellar travelers are the rough drafts of planets that never finished forming. About the meeting in the solar glare. Solar conjunction is a real problem for observation. When objects pass close to the sun, from our point of view, radio links drop and optical telescopes get blinded. This happens to Mars missions almost every 2 years. NASA's Deep Space Network pauses some communications on purpose to avoid frying antennas. So yes, there's a blackout window, but it's not a cover-up. It's a safety rule. If SWAN and 3I, Atlas, pass near the sun at the same time, we lose eyes on both. That feels dramatic, but it's just geometry being annoying. People also worry about why agencies go quiet. The boring answer is peer review and caution. JPL and ESA scientists don't like to speak in public until numbers are checked 3 ways. Early estimates change. Models get revised. Hubble spectrograph records get reprocessed. When agencies say less for a while, it's usually because they're busy arguing with each other in meetings, not hiding a secret fleet in the sky. And the ancient myths? Humans have always turned bright comets into stories. We link sky events to big moments on Earth because our brains love meaning. Babylonian tablets, medieval chronicles, Chinese records, all of them mention bright tales and strange colors. That doesn't mean those comets were the same object coming back. Orbital periods of tens of thousands of years make repeat visits nearly impossible to match to written history. It's more honest to say, bright comets scare people, and scared people write them down. Here's the calm truth. SWAN looks huge because it's close and active. 3I, Atlas looks agile because it's venting fresh ice. Their timing feels spooky because our detection systems finally got good enough to catch more than one interstellar visitor in the same decade. None of that requires a mission plan. It just requires a big galaxy, lots of debris, and better telescopes. If there's a real mystery here, it's not about intent. It's about origin. What kind of star system made SWAN? Did it form around a red dwarf or a sun like ours? What kind of ices and metals get packed into interstellar objects? That's the science that James Webb, ESO, and future Rubin Observatory surveys are chasing. Those answers tell us how common planet building is across the galaxy, and by extension, how common places like Earth might be. And once you follow that thread, the story gets deeper without getting scary. The Vera Rubin Observatory in Chile is about to flood us with data we've never had before. When its survey fully spins up, it will spot faint, fast movers crossing the sky every few nights. Not one interstellar visitor every few years, but dozens over a decade. That alone will change how rare these events feel. What looks like a once-in-a-lifetime moment today may turn out to be the tip of a quiet, steady stream we were blind to before. James Webb adds another layer. Its infrared vision doesn't just show glow. It shows what these objects are made of. When Webb breaks down the light from SWAN or 3I, Atlas, it reads the fingerprints of water ice, carbon compounds, silicates, and metals. The Harvard-Smithsonian Center for Astrophysics has been comparing those fingerprints to comets from our own Oort cloud. Early patterns suggest interstellar bodies aren't foreign machines. They're familiar stuff made in unfamiliar places. Same ingredients, different kitchens. There's also a simple reason energy outputs look wild at first glance. When volatile ices heat up fast, jets can spike. Hubble spectrograph records of comets like Hale-Bopp showed sudden surges that fooled early models into thinking something new was happening. Later work showed it was geometry and timing. When jets line up with our view, brightness jumps. When they don't, it fades. That makes some bursts feel rhythmic, when they're really just rotation, bringing active spots into sunlight. Voyager 1 telemetry data helps here too. Out past the heliopause, Voyager has been sampling the boundary where the sun's influence fades into interstellar space. It measures dust density, plasma, and magnetic fields. Those readings show our solar system is moving through a messy neighborhood full of leftover debris from ancient star systems. That debris doesn't travel alone. It drifts in streams shaped by gravity and magnetic fields. When one stream lines up with our orbit, we notice more visitors close together and think something big is happening. Most of the time, the stream misses us, and we see nothing. Even the idea that two objects arriving together is impossible doesn't hold up once you run the numbers over millions of years. The European Southern Observatory has run long simulations of how interstellar debris flows through the Milky Way's spiral arms. Clumps form. Not tight fleets, but loose clouds. When the sun crosses one of those clouds, we get a spike in interstellar passersby. It's not a mission, it's traffic. So here's the part that actually matters for us on Earth. These visitors are free samples of other star systems. We can't fly probes to every distant sun, but nature sends us pieces. By studying SWAN and 3I, Atlas, scientists at NASA, JPL, and Keck Observatory can test ideas about how planets form, how water moves between systems, and how common the raw parts of life might be across the galaxy. That's the real treasure. Not fear, not secret plans, knowledge. And there's one more thing most headlines miss. None of the current models show either object coming close to Earth. They pass through, light up the sky for a while, then fade back into the dark. No impact paths, no near misses with our planet. Just brief visitors, like ships passing in the night. Except they're not ships, they're rocks and ice with a long memory of places we may never see. The universe is loud with stories, if you know how to listen. Not every loud story is a threat. Sometimes it's just the galaxy reminding us how big it is and how small our little neighborhood really looks from the outside. For a brief window, everything lines up. SWAN and 3I, Atlas, slide past the sun. Our telescopes straining at the edge of what glare will allow, data pouring in from the James Webb Space Telescope. Hubble spectrograph records filling gaps we didn't even know were there. Teams at NASA Jet Propulsion Laboratory and the European Southern Observatory watch the numbers settle, not into panic, but into clarity. The paths don't cross in some secret meeting. The energy spikes smooth out once geometry and rotation are factored in. The bright flares fade into patterns we've seen before in comets like Hale-Bopp, just amplified because these visitors are fresh, fast, and loaded with volatile ice that hasn't been baked by our sun before. The impossible begins to look rare, but real, strange, but still part of nature's playbook. And in that moment, the fear drains out of the room. What's left is awe. Two messengers from faraway star systems passed through our sky at nearly the same time. And for once, humanity was ready to notice. Not to fight, not to hide, just to learn. So here's the truth that sticks with you when the headlines move on. The universe didn't send us a warning. It sent us homework. These objects carry the chemistry of other suns, the history of other worlds, and clues about how common the raw parts of life might be across the galaxy. The Vera Rubin Observatory is about to make moments like this feel less rare, and Webb will keep turning faint light into hard facts. We're stepping into an age where interstellar visitors won't be myths or scares, but data points that slowly teach us who we are in a much bigger story. The sky didn't change to threaten us. It changed to show us how much more there is to understand. If you want to see what Webb spots next and how these visitors rewrite what we know about our place in the galaxy, watch the next video on your screen and subscribe so you don't miss what's coming.